One thing we often do as chemists is use different acids because they have different properties, they have different strengths, they have different abilities. But how do we understand the strength of an acid? You should be able to predict the relative strength of acids and bases based on their molecular structures. Now, if you've got a Ka or a Kb value, it's relatively straightforward to predict the strength of an acid or a base because the Ka-Kb value is telling you that, right? A Ka value is telling you how much of that acid is actually going to dissociate at that temperature. It's telling you your percent ionization. But what if you don't know that value? Or what if you have strong acids or strong bases? How do you really figure out what the strength of that acid is? So we need to be able to predict the relative strength of acids and bases based upon their molecular structure. You should also be able to describe the leveling effect and understand how this is applied in aqueous solutions. Acid strength. Acid strength refers to the ability of an acid to donate a proton. How likely is it to donate that proton? So again, this goes back to Ka. Remember, Ka is going to be the concentration of your conjugate base times H3O plus divided by the concentration of your weak acid. Or if you have a strong acid, there is no Ka, it just dissociates 100%. But how likely is it for that acid to donate that proton? And for base strength, this is the ability of the base to accept a proton. If we look at Kb, we can say this is equal to the conjugate acid that is formed after donation times the concentration of hydroxide divided by the original concentration of our base. Or if it's a strong base, we just know it is a strong base, but how do we predict the relative strength of these? There are two important principles that you have to keep in mind when doing this. First, the stronger an acid, the weaker its conjugate base. What do I mean by that? Well, I mean, let's use HCl. It's kind of my go-to acid because it's just it's simple, but it's strong. HCl is a strong acid. We have memorized it as a strong acid. Why is it a strong acid? Well, we've told you it's because it dissociates 100% into H plus ions and Cl minus ions, which means if I had a 0.25 molar HCl solution, I actually have 0.25 molar H plus in solution and 0.25 molar Cl minus in solution. Great. What does that mean? It means that the conjugate base is weak. Remember what a base does. A base accepts a proton. And some people think about a base as stealing the proton from the acid. How likely is that base to take that proton? Cl minus, your chloride ion, is so stable that it doesn't want that proton. We've talked about this in first semester. We learned about electron configuration and how everyone wants to be like a noble gas. Chloride ion has its noble gas electron configuration. There is no reason for it to take back a proton. It has everything it wants. It has its complete octet. It has a negative charge to boot. It is an electronegative element. It's the tied for third place for most electronegative element on that table. It is quite happy. It does not want a proton back. Therefore, it is a really bad base. It is a poor base. It is a weak base. The stronger the acid, the weaker its conjugate base. The strength of the acid is determined by the stability of its conjugate base. The stronger the acid, the more stable that conjugate base. Cl minus is incredibly stable. There is no reason for it to react. So, anything that stabilizes the conjugate base will make the acid stronger. What can stabilize this? Charge delocalization. What do I mean by charge delocalization? I mean size, and I mean resonance. So when you think about size, we know HF is a weak acid. We know HI is a strong acid. Well, F minus is really small, right? Our nucleus, and let's pretend that's a circle. Our nucleus and our atom is pretty small. I minus, on the other hand, is huge. I have delocalized that negative charge. It's a more stable base because of charge delocalization. F minus is weaker because it's not as stabilized. Another thing to think about here is resonance. Let's look at HNO2, weak, and HNO3, strong. Remember, the NO2 ion is called nitrite. So this is nitrous acid. NO3 minus is nitrate. So this is nitric acid. And if we think about the resonance structures of the conjugate base, so if I lose a proton, it's going to form this or this. NO2 minus has 2 resonance structures. Whereas NO3 minus has 3. And I'm not writing these out very well, I apologize. But this has 3 separate resonance structures. Therefore, it's more stabilized, more charge delocalization. Therefore, its conjugate base is more stable and less likely to take a proton back. Therefore, a stronger acid. So, some nice charts for you guys, just kind of, these are straight from your books, you can find them there, but I really like them, just kind of showing you the acid and its conjugate base. And its general strength. So your strong acids, their bases are pretty neutral. H3O plus is the strongest acid that can exist in aqueous solution. We'll talk about that in just a few slides. And you can see that as we go down to negligible in acid strength, those become your strong bases. So molecular structure and acid strength. Again, we see here, we decrease strength as we increase in acidity, as decreasing down and decreasing across. These 3 here are our strong acids. And that is because of charge delocalization. Well, it's 2 reasons actually. It's because of charge delocalization and electronegativity. But we need to talk about 2 different types of acids, binary acids and oxyacids. In binary acids themselves, and that's what this chart is looking at, is binary acids. Binary acids contain only 2 elements. They have hydrogen and one other element. The neutral binary acids from the table include what's in this chart, but it's your CH4, NH3, and pH3, H2O, H2S, H2SE, and H2TE, and I apologize, I'm starting this on a whiteboard, HF, HCl, HBr, and HI. As we go across and down, we increase strength. Now, some people may say, but ammonia is not an acid, it's a weak base, right? Yeah, technically it could donate a proton. It doesn't like it, which is why it's such a weak acid. It's a better weak base. It doesn't want to give up its proton, but we could make it. That's why it's increasing as we go across and down. So why does the acid strength of binary acids increase from left to right? If I go left to right, we can see here we're increasing electronegativity. Why does it increase as I go from top to bottom? If I go from top to bottom, we're increasing because you're increasing size. Increasing size means increased charge delocalization. Remember, fluorine becomes fluoride, which is really small. Chlorine becomes chloride. Bromine becomes bromide. And iodine becomes iodide. So why is HF a weak acid? If I say it's increasing as I go across the table, it is. But it's so small that it doesn't have charge delocalization. So it's still a weak acid. It's still not going to get rid of all of its protons. It's still going to behave as a weak acid. HCl, on the other hand, is like, nope, take it, we're fine. So let's work a few example questions. What is the stronger base, pH2 minus or HS minus? Well, strongest base means that it wants to accept a proton. The stronger the base, the weaker the acid. They are inversely proportional to each other. So pH2 minus comes from pH3, and that should say HS minus, I apologize, comes from H2S. If I look at these two on the table, this is going this way. So H2S is a stronger acid. Which means that pH3 weaker acid. pH2 minus stronger base. It's more willing to accept that proton back. It's less likely to want to lose that proton. It wants to keep it more than H2S does. What is an oxyacid? You guys have seen oxyacids your entire Gen Chem career so far. You may just not have realized that that's what they're actually called. An oxyacid contains hydrogen, oxygen, and one other element. The trick is that the acidic hydrogen is always bonded to oxygen. The oxygen atoms are bonded to your central atom. So this is like H2SO4. HNO3. H3PO4. I don't usually put all the Lewis dots, but I know sometimes students see them better with that. These are all oxyacids, where the hydrogens, the acidic hydrogens, acidic meaning the hydrogens that are going to be pulled off. Are going to be connected to an oxygen, which is then connected to a central atom. For oxyacids with the same number of oxygen atoms, acid strength increases as the electronegativity of the central atom increases. So, H3PO4, H3ASO4, H2SO4, H2SeO4, H2TeO4, HClO4, HBrO4, HiO4. Increases across and up. How do I remember this? Because I know that out of this entire list, these two are strong acids. If these are the only strong acids, then that suggests to me it's across and up. And then I remember electronegativity. For oxyacids with the same central atom, acid strength increases as I increase the number of oxygen atoms. So, for example, H2SO4 is stronger than H2SO3. HNO3 is stronger than HNO2. HClO4 stronger than HClO3, stronger than HClO2. Why? As I add more oxygens, I have more resonance structures available, which is stabilizing the conjugate base. The more stable that conjugate base, the stronger the acid. Because I ran out of room on that side. For example, which is a stronger acid? HBrO2 or HIO? Well, we got two things going on here. We've got the different number of oxygens, but also different central atom. In this case, this one's going to be stronger. First of all, bromine is more electronegative. Second, this has more oxygens, so more stable conjugate base. Please be careful with this because binary acids and oxyacids with the same number of action atoms do not follow the same trend. Binary is across and down because we're looking at stabilization. Oxy is across and up. Both of them do it because of stabilization of that conjugate base. Electronegativity, charge delocalization, resonance. But the presence of that oxygen makes it behave a little bit differently. So be careful and either the best thing to do is fully understand why and be able to identify why. But if you're just going based on trends, be careful with your trends. Last thing we want to talk about is the leveling effect. So, HCl is actually a weaker base or weaker acid than HBr, which is a weaker acid than HCl or HI. So what happens in aqueous solutions? What is the strongest acid that can exist in aqueous solution, and what happens to acids stronger than this? what is the strongest base that can exist in aqueous solution? What happens with bases that are stronger than this? The leveling effect happens. Basically, we've talked about when I put HCl in water, it immediately dissociates into H plus Cl minus. But saying H plus is not quite correct. What's actually floating around is H3O plus. So this proton is scooped up by a water molecule to form hydronium ion. The strongest acid that can actually exist in solution is hydronium ion. HCl does not exist in aqueous solutions. HBr does not exist. Everything is creating hydronium ion. Now, this used to really mess me up. I never really understood what this meant. So I was like, but these are stronger acids and hydronium's not that strong, comes from water. I don't understand. What I need you to think about is if you have a beaker of just water, you naturally have floating around in solution H3O plus, OH minus, and H2O. But at pH of 7, we know that our H3O plus concentration equals our OH minus concentration, and this equals 1.00 times 10 to the minus 7 molar. When I add HCl to this, it's basically just increasing the concentration of H3O plus. So I have more of them floating around in solution. Hence, the pH decreases. The strongest acid that's actually existing the whole time, though, is still H3O plus. I just have more of them. It increases this concentration. It decreases the hydroxide concentration. The strongest base that can exist is hydroxide. Sorry, I was reading the word hydronium. Hydroxide. Any base stronger than this is leveled down to react so if you've got NaOH, it forms Na plus and OH minus. It's just increasing the hydroxide concentration in solution. So even though I put strong acids in, they don't stay together. They completely dissociate, or 100% ionization if strong. And if weak, they still kick off a proton or form hydroxide, which is just changing the concentration of these species that was already in water naturally. We call this your leveling effect. The strongest acid that can actually exist in aqueous solution is just hydronium ion. The solution itself is more acidic because we have more of it, or a higher concentration of H3O plus as compared to neutral water. If we add more base, same thing. The hydroxide concentration is just greater than the hydroxide concentration from water itself. And that's known as a leveling effect.